Hi, this is Josh again with Calculus 1 tutoring, uh, creating a tangent line for a function. Here we have an application for first year physics. The function is tracking a projectile, f of x equals 400 minus 16x squared. I've shown this as a projectile, such as a standard student problem of, say, a cannonball launched from a cliff at a height of 400 meters, and then tracking that object from time equals 0, the firing of the cannonball, to the time t equals 5, the impact at sea level. So as you can see here, if I turn on the animator, the cannonball will start at the top of the cliff, and then the projectile will fall off and increase in speed until impact at 5 units of time. The problem here you can see with the tracking circle is that there's a change in y of 400 units, but the change in x is only 5 units. Here in the window, that's 500 units delta y, and in this window, that's 50 units of delta x. 500 divided by 50 for this window would be a window ratio of 10. So in order to correct that, here I'll pause the animator, I added the ellipse formula for the y component here into the circle equation. So here you can see x minus a squared will make the center of the circle at a, y minus f of a will make the center of the circle at f of a, so a f of a. But if we divide by the window ratio, here it's set at 50, but it should be 10 because 500 divided by 50 is 10. Then it will transform it to a circle. Then, since now it visually looks like a circle because we offset the eccentricity of the window that created the ellipse, make sure that you also do that with the formula. So for the hypotenuse of the within the work circle from the center to the edge of the circle, we'd have 1 plus f prime of a squared, f prime being negative 32a. Here I actually wrote it in, divided by the window setting w, which is also squared. So it's negative 32a over w squared. Also do that for the offset on to the right side of the center point. So that's this point up above and this point down below. Then as the circle tracks, it will you will get a diameter that's truncated properly. Here the circle is rather small, so I'll increase it to the maximum size, 10, giving a diameter of 10 for the circle. The window scaling really does work. Here, I'll pause this again, but the picture might not be good for a presentation. So here, I take the same function with the same domain restriction, but for the presentation here, I have 500 units for my delta y still, because then I can see the full arc vertically. But instead, I go from -2 to 8. Now that's just 10 units along delta x. So 500 divided by 10 would give me a W ratio of 50. So then if I set the slider at 50, you can see we get a much nicer picture where we see the arc with the cannonball being launched with a little bit more horizontal velocity. So it seems, because this is actually the time axis, but it creates a much nicer picture where we can also see the cannonball from the top of the cliff and then smashing down at impact at t equals 5 seconds. Again, this is my work circle to guide and space out that diameter. If I turn that off, students can see the changing tangent line for this projectile. Since this is an application to physics, we have the time axis versus the height. We might also want to plot the point f prime of a down below, because that has meaning in the physics model. We set t equal to 5 seconds, for example. We see that, okay, for this cannonball that was launched at 400 meters, at time 5 seconds, the height is 0. But we're also told that at f prime of a is negative 60 meters per second, meaning that that cannonball, which was launched from 400 meters, now has a velocity or speed of negative 160 meters per second. From there, you can calculate the momentum and other components, and the impulse and other components for your physics class. So I hope this video was useful to you for your studying Calculus 1 and applications here for this projectile. Thank you for watching my video, and happy studying.